Thank you for the opportunity, and I'm a little bit jet lagged from last few days of travel and not sleeping thanks to NSF panels, but that's life for all of us. So, when I learned what you guys were doing and where you were headed, sort of data science just as a concept, that's something that I've been teaching and working with at scale with life science researchers. As a background, I'm an engineer, a systems engineer by training, but the last 25 years of my life has been being embedded with life scientists and then building infrastructure that was focused on improving computational productivity. Astronomy as a community, from where I came 20 years ago or even today, was far more advanced in terms of what you guys were doing as compared to me pulling a graduate student from a molecular lab. And now sometimes I compare it the other way, where I say, when you look at cell phone service in the US and then you look at Africa and you say, wow, I have better coverage when I'm traveling in parts of Africa. What just happened? Well, they never had landlines and they bought straight up into the mobile world. Life sciences was sort of the Africa where we didn't really have landlines and we just went to mobile. So the whole concept of cloud native is very prevalent and relying on somebody else's resources, because none of them had the clusters that they could access very readily. So it's a very different sort of mindset, but I'm now sort of seeing the convergence. So I'm not here to talk about cybers. I'm here to talk about the resources and the challenges I've seen sort of my students and the users. Cybers has close to 40,000 users, out of which 5,000 are active. A lot of people registered but don't come back and use for various reasons. We have about 2.5 petabytes in Tucson, all user contributed. They bring it through the university networks. Most of our users can handle 10, 20 terabytes without asking questions. They know how to move and manage that scale of data. The part that always gets to them is going from the laptop to a different system. And I've seen more people spin wheels because that deliberate planning was not there. Maybe 2 years ago, 3 years ago, 5 years ago, it was extremely hard, but today, going from your laptop into an HPC world or even the cloud is fairly straightforward as long as you follow certain secret handshakes. And I'm here to talk about some of those secret handshakes. And I want to keep this sort of very informal, where stop me, ask me questions. And towards the end, I want you guys to start using one of my other projects called Jetstream, and it's a cloud that's available to all of you guys. And so there's a piece of paper that will go around. Where did I put that? Oh, here it is, sorry. I would encourage you guys to do it as a pair, so just put your name. The password is right there, and I'll tell you where to go to get started. So I'll start from here. So if you guys can share a login, that's good enough. I mean, don't log in together simultaneously, but work with each other and pair up. Okay. So, come on. Why won't it go forward? Okay. So what I'm going to cover is sort of the very standard innovation life cycle and where I see challenges. How many of you have heard of the term computational thinking? No? Okay. I want to talk about computational thinking, and it's not about thinking like a computer or AI nonsense. Then I want to talk about, oh, this is being recorded, that's what I have to be here. NSF infrastructure that you have access to. What I found is a lot of people either have knowledge of it from 20 years ago or 10 years ago when somebody in the lab tried it, and that knowledge has remained, but the technology changes every few years. And so understanding what's available to you and getting access to it. And it's actually pretty straightforward. There's always sort of the air of it's too complicated, it's too hard, nobody gets it. It actually, there is a way to get it, and you just have to know how to formulate what you want and ask the right questions. And again, we'll talk of the handshakes. The technology landscape, and I'm going to talk a lot about cloud and containers. How many of you know what containers are? As in computational containers. Okay, so 2 people, 3 people. Which containers have you used? Docker? Okay, anybody else other than Docker? Any Singularity? Okay, we'll cover that. And I saw you had sort of a quick overview of cloud. How many of you are familiar with cloud infrastructure? Know the difference between a instance, an image, a volume, a bucket? No? We'll just like fly through those things. And then we'll do hands-on part of it. And we can keep it completely open. I have something that I want you guys to try. I looked up the Git repo, and you had a notebook from yesterday, one of the sessions. Maybe we just bring that notebook in and look at it in the container, and I'll show you how easy that can be. So here's sort of simple formula for success. You usually have a good idea. You show up in the lab meeting, and you convince everyone that you read this paper. It's awesome, and we should be analyzing our data this way. How many of you sort of been through that? It's a very common life science thing. We have like lots of journals. So like every week there's somebody with some cool thing, and then you want to do that, and then you have to convince your whole lab to do that, and then the PI says, you can try it out, and then somebody says, just put that in the cloud, it should be fine, and there'll be fame and fortune for the whole lab. Well, what really happens is you read the paper, then you realize there's Excel, there's R, there's Perl, there's Python, Jupyter Notebooks, Java, and you can also add your favorite machine learning methods, Spark, Hadoop, and there's lots of glue involved. You're like, I think I can handle that. And then you say, okay, I can run that in the cloud, but then I have a laptop that's Mac, some of the binaries are Windows, and all has to run on Linux. And where do I run that? Oh, you can run that on Amazon, on Azure, on Google, your campus, XSEDE. So all of a sudden, what you thought was I can git pull, compile, run, and feed my data became this absolutely onerous exercise. And you start asking people questions, you start contacting the author, and I like to call it sort of the first author syndrome, because at least in our discipline, the first author is the only one that really compiled, tested, and used it. Everybody else just was touching the laptop or watching it or something of that sort. And so you start harassing that author, and the author starts responding to you. You start begging to other people in the lab how to compile something in Fortran, and they sort of defriend you, and life becomes complicated pretty quickly. So what you thought was an idea plus the cloud becomes something like this, and lightning bolts strike you. The PI says you're no longer a productive member of the research team. You're a drain, and you're a disappointment, and your ideas are the bright ideas, as you can see. I know it's too soon to make EPA jokes, but we know what happens when something like this shatters. And this is important to note, because what I see is the innovation actually starts from somebody in the lab who's really enthusiastic and is thinking out of the box, trying to read something and bring that into the fold. But the overhead to do that is so high that as you are spending more time in the lab, there are more people discouraging you, not because they don't like you, but the technology has failed them. And I consider that sort of from my perspective, where I built some of these technologies, that we've done a horrible job where we've given people sort of the, hey, you can do this, you can do that. And when they really try it, we trip them up with things that are just completely outright stupid, and it should be done differently. So we'll talk about what we are trying to do differently. So there's a lot of demand on your time. You have open innovation, open science. You guys are all trying to work as a team. And if somebody tries to tell you data science is a single person activity, so if you're doing everything all by yourself in your lab, most likely you're not doing data science. You're just doing your regular science. Okay? Data science, you are going to work as a team. There are going to be more people poking at your code, asking you questions, pointing you to 10 different things, and you have to work as a team. Not everybody in that team is going to be on the same page ever, but it's your job to convince everybody to be on the same page, whether it's the analysis or the profiling or the versioning, whatever it may be. The complexity of the infrastructure, which we'll talk about, and the evolving technology landscape. It is changing. So what you saw today with Zeppelin or with Spark, the next version will be around the corner, and you have to be organized enough with your data and compute so that you can adopt that, validate what you're doing with the new version, and use it. If you say, I'm going to be stuck with version X of this tool, most likely you're not trying to get your science done in a way. Now, reproducibility is important, but the way you're going to be starting to do that, if you don't follow it and bring in the new version, there might be bugs, there might be things that are stopping you from achieving what you need to. So being organized, whether it's your Git repo or your data or your workflow systems, they all have to work in unison. And then do you know where your data is, where your metadata is, where your analysis done by somebody else is. You become sort of responsible for that. And we are in the age of extreme information technology. Not everything is produced in our lab. It comes from Facebook, it comes from someone else. And it's very easy for a dozen engineers in Facebook to write that blog and say, whoop-de-doo, we did that, Netflix did that. And then you and your lab mate are like now responsible for doing what a dozen software engineers working full-time in Silicon Valley did. Now it's not that easy, but you can make it easy. But there's a lot of cool things coming out, and if you position yourself and design your workflows, your data, your computation to leverage that, you will benefit from it. Now there's a caveat to that. You don't have to be a fanboy or a fan person running around and say, oh, Netflix has a blog, oh, Google said this. You have to be able to assess that. And that's where, again, the data science part comes in. If you are a cohort of people working together, one of you could be responsible for the technology assessment and then share your knowledge with the rest, so that everybody else is not trying to install Kafka and say, streams with Kafka, I love it, but it doesn't work for us. What doesn't work? Maybe somebody can fix that. So the idea of collaboration is big here. And you have to be willing to change your computational platform every 3 years. That's sort of my own personal number. There's now like papers that support that. But the way I work, every 3 years, I have to be prepared. Either the architecture is changing for the software, or the language that I'm using is deprecating some function. Bad stuff is happening. So I have to be ready every 3 years to redo something. And maintenance is the focus. Software is not write once and forget. I'm going to talk about technologies that will allow you to do that, but end of the day, software lifecycle management is crucial to sort of your scientific pursuit. So keep that in mind. Here's the landscape. I'm not making this up, okay? If you look at it, you pretty much will go cross-eyed, and then you have to decide, I want to use this OS with this database running here, automated by this. And so by the time you sort of weave your way through this maze, you're pretty sure there's something that's broken or a security patch that came out that will essentially stop you from using it. And so we'll figure out how to take care of that as well. So now let's talk of infrastructure. Okay, NSF XSEDE invests $121 million every 5 years. That's a pretty good chunk of change that goes in. My own university, how many of UFA people are here? 1, 2, okay. Almost 2, 3, yes. Okay. It invests $2.4 million every 3 years, which is also pretty sweet. You get a good system every 3 years, and there's a lot of resources. What's common between both of them? They are free. They're available to you at no cost. What you would spend, and I know running something on Amazon or Google will be $3, but when you scale it 1,000 times, it is $3,000. If somebody's giving me $3,000 worth of compute, I am going to go use it. And I'll use the free ones also, and I'll talk about how to combine them. Okay? And so we sort of become data rich and knowledge poor, and it's the same is true with infrastructure. We have so many options, and I kid you not, you're going to find people who have resources that are not able to leverage them. They will have a system where the cluster is spinning wheels on 20% of the resources, the other 80% are not used because they haven't optimized their code, or they haven't, had the job submission command line include something which says, use all the processors I get. Like small things, but nobody looks at that. They just take the code and say, you gave it to me, you're awesome, you ran it on your system, must work on the UA system. And you just run it, and you realize that you were running it okay, but you were using half of it. And that's a whole other conversation. So now let's get into computational thinking for scalable science. So computational thinking as a concept, Janet Wing, who think in the middle 90s, was at NSF, she's at Carnegie Mellon, and computer scientists have put a lot of thought in looking at questions and abstracting them and trying to solve them. And so I think she herself, at that point, might have been the department head of CS, and she felt that all the disciplines were becoming more and more computational, and that process of looking at a complex problem and working with it required that same rigor, the same thought, the same considerations to architecture. And she proposed these 4 A's, which I live by for computational thinking. The first is abstraction. You take your question and you abstract that away into multiple layers. Then you think of automation, of how you're going to automate whatever exists in the layer, and how you're going to go up and down the layers, which eventually gives you the ability and, most importantly, the audacity. And the reason I really care about the audacity is I have seen too many people in my discipline live in their laptop. And by that, what I mean is they scale their thinking down to what the laptop can do for them. They reduce the question to their laptop, and that's the worst thing you can do as a scientist today, or as a data scientist that you're being trained as. Your world is much, much bigger, and you should have the audacity to ask the question, but at the same time, not be absolutely foolish and say, I will solve this problem. You want to understand the complexity, and the complexity is better understood when you do the abstraction. And this is sort of, again, out of scope for what we're talking today, but I want you guys to keep that in mind. And that allows researchers and educators to establish and manage data-driven collaboration. Whatever you're going to do is going to be data-driven, and you have to work as teams and virtual organizations at global scale. I mean, I don't have to explain it to you guys live in that world, but for my community, it was, I own everything end to end, and I don't need to talk to anybody else. So this sort of changes. And then you make efficient and coordinated use of CI, which is cyber infrastructure resources, national, regional, institutional, and commercial. Do not leave anything on the table. Consume everything. If you get the $100 card, this is being recorded, I'm going to be in trouble at some point. I tell my students, go get the $100 card from Amazon and use it. I want you to know how to use it really well and get the maximum throughput from that $100. Google's giving you 300, go get it. Don't leave anything on the table. You have something on your institutional infrastructure, you have a monthly quota, go use it. Don't let anything go to waste. And then there's a lot that's at NSF world, and my project used to be called iPlan, now it's Cybers, and we are sitting on amazing bandwidth. But when I look at people moving data, they still use FTP or SFTP. That's one step better. But when you start working with terabyte scale, that doesn't work. And then you start arsing jobs, and then you start losing. There are other techniques that are available, and getting people to understand what a data transfer node is, how do you move things around, how do you apply metadata, how do you search things by it, or if you're moving to an HDF, as in not to be confused with the HDFS, but HDF5 or NetCDF instead of FITS, what do you get in return and how do you do more with it? Okay. And then you adopt best practices from other science domain where these things are solved, whether it's in high energy or it's in life sciences. Go back, borrow, steal from someone else and do more with it. And you have to look at things that are community driven, self-provisioning and extensible. And that's one of the reasons I like the cloud, because it gives you a lot more control that is with you. You have control of the OS version, the dependencies, and with containers, a lot of that is coming to HPC, and we'll talk about it. And then open source is what I live by and I subscribe to. And then, do all of this in a way where you are working with the computer and information science community. That is one thing that I see a lot of people not actively use. When I work at a university, for me, it's like I'm in the best startup that can gather all these people. So if you have a question, walk over to the CS folks, find a grad student there, start talking to them, buy some beer. That's like the least investment you can make in someone. And then they will suggest things that you would have never thought of. You're talking of indexing. There are like 10 different techniques of indexing, but you're only going to use the one that you know that's available in MySQL or Postgres. But there'll be a bitmap index that is available through some other method. And I have had so much good luck just chatting for half an hour with that person to learn new things. So again, important to sort of go find those friends and build that network of colleagues on campus and beyond campus. Okay, so I'm going to fly through. I've taken a lot of time. So XSEDE, how many of you have heard of XSEDE? Okay, this is being recorded, so I know some of you may not say. How many of you don't like XSEDE? They cannot see, they can only see me. Raise your hand, it's completely okay. Okay. What is the experience you had that you didn't like about XSEDE? Again, they only see me, not you, so say it. Tell me what is challenging.
For me, I was running into problems with like the allocated times, and just like how you were distributing your notes and things like that. But yeah.
Were you able to get any help when you asked?
Sometimes.
Sometimes. Can you tell me which machine you were on?
Stampede, I believe.
Okay. Yeah. Anybody else?
I used Kraken years ago.
Okay.
It was okay.
It was okay.
I've had really good experiences using. I've had really great experiences using Gordon.
Gordon, okay.
Same there. So I've been using tag directly, but through XSEDE not so well experienced.
Okay. Cool. So when I wrote Cyverse as my project, NSF looked at NSF Bio and said, hey, we're spending billions of dollars, people gathering data, the analytics is lagging. When I got that funding, which is a good amount of funding, I said, I'm not going to duplicate what other people are doing. I'm going to find out where the gaps are, and I'm going to build middleware to fix that. Okay. And when I looked at XSEDE, they have a 3-year cycle of doing new things. And I knew what I liked, and I knew what I disliked. Like, for example, I needed an API to submit my job. This is just like ridiculous that I have to log into things and do that. And they said, API, what is that? Go away. And so I said, no, I'm going to write RESTful APIs to talk to. We had to go through the security review, but they did that. And so if there's something that doesn't work for you, the first place is to formally explain that, not emotionally, but with facts. Facts are stronger than emotions. And when you explain why something is not working for you. And then there's a group within XSEDE called Extended Collaborative Support. There are some people who are really awesome in there, and you should sort of keep that name among yourself and exchange that and get help from those people to either design a workflow system or a workflow engine around what you do. Because 90% of the time when you're battling with limitations of hours or time, if you were using a workflow engine, you can do a lot more distributed computing in a multi-location way, and we'll talk a bit about that. So most of you know what XSEDE is. NSF buys good infrastructure, puts it somewhere, and then you can get access to it. It's pretty much leading edge. You get large systems. How many of you guys are MPI based, like you do computations that need MPI? Okay. How many of you just need straight up raw like CPU, and you need like 64 gigs RAM or something like that's sane? Okay, a good chunk of you. Okay, for you guys, open science great as long as you are willing to sort of get kicked off and you write your workflow systems. You can do really interesting things with it. We run 4,000 or 5,000 concurrent jobs, and you can get them fairly quickly, but then if you're going to squat on it for 3 days, you're in trouble. Your job should be like in a few hours, and then you have a system that manages that. Lots of interesting, and you guys are doing machine learning, so eventually GPUs will show up in your lives if they haven't yet. And so you get really good systems. Cloud services, one of the first projects is based on the work that we did, and I'll talk about it, and you guys will kick the tires around. So here are the systems that are there. I'm not going to go through it. I put a link to my slides. This is what you can get. There's a lot of training and user engagement that they're working extremely hard to improve that. And I am funded through some of the XSEDE activities, but I found I follow the same queue. I stand in line just like anybody else, or even the systems that I'm a PI on, because it's everybody's system. And I've learned that when I want help, if I don't ask the question correctly, I don't get it quickly. And this is something that is for all of you guys, is learning how to file a bug report, how to provide the background for it, and how to understand the system so that somebody can reproduce what you're doing so that they can help you. What I find, because I read the tickets I get, which I do on my systems, and because that tells me a lot about what I'm not doing correctly, is when people say this doesn't work, or this crashed, or this sucks, and my paper's due next week, you guys are horrible, those don't help the cause. But if you say, here's my code dump, here's my previous run, here are the metrics, here's what I saw, this is what I'm observing today, why is that, or can you help me diagnose that, you're going to get someone who's willing to pick up that ticket much sooner than you guys suck. So that doesn't happen. So here's sort of the portal, you can go figure it out. You get HPC, you get data storage, you get Viz. Again, connect to the collaborative support. Allocation requests are actually, the startups are really easy. How many of you have written your own allocation requests? Okay. And did you get your full or startup? What did you get?
80% or something like that.
Oh, okay, and this was on Stampede? Okay. Startup allocations are actually pretty easy to get. So like getting 200,000 compute hours, which is a decent chunk of change on a system. I usually talk to the person for that system and I file a question and say, I'm trying to do X, would that be good on your system? And they usually will come back and give an answer and they'll give you some ideas. And I'm like, can I submit this with this? I'm being recorded, I'm going to be in trouble, I don't know where this is going to show. But when you talk to the person who you ask the question, 75% of the time that's the person that's reviewing your proposal. So there's already like, oh, this student was so good, they'd ask me this question. Check. So education allocations are really easy to get. They like it. So if you guys are doing a workshop and you want your own flavor of Hadoop on Wrangler, go get it. I'm happy to help you guys get more. I love when students can do some good scalability work. Longer allocations, like million hour plus, you have to do a little bit extra work. And there are lots of webinars on how to write successful ones. Okay. And I know for your community it's hard. For my community it's very easy to say, oh, we're going to do this with the rice genome that will feed 9 billion people, blah, blah, blah. So there's a lot of like sympathy that goes with it and to the reviewers. But now the honeymoon period for the biologists is over because there are so many of them in the queue that they're like, well, yeah, your question's not that awesome. Next. So there's a lot of training that goes on. So sign up for that. You can get help via. And has anybody called this number? They're actually pretty awesome. So I had to get the password for you guys, and I was in DC. It was like god awful, like 1 a.m. in DC. And I think this number is in Indiana or Illinois somewhere. And I called up thinking I'll get voicemail, and it's like a human being. And I said, hey, I'm calling for the passwords. I know they've been ready. And they're like, oh yeah, we are waiting for your call. Here's that service. So they're pretty good people. Okay? And so there are a lot of student programs. There are underrepresented minority activities that they do, community infrastructure. They have campus visits. They also have good conferences that you can go see and present some of your work. They have an online HPC university with workshops. How many of you know who a campus champion is on your campus? Anybody know? Okay. Find that person on your campus because they have access to resources. And most people don't know the campus champion, so the resources just sit there. If you show up in their office, you get them. Handshake number 1. Okay, so the other parts are, they'll help in other aspects of it. The campus champions are people who raise local awareness, provide training, provide feedback, and then they share material and they build the community around their campus. It's very helpful when you have trouble with Stampede and the person on your campus has figured out that secret handshake. You know who they are, and then you can sort of help each other out. So now I'm going to completely switch gears, and before I do that, any questions about what I've covered so far? Okay. Why containers? First of all, I'm wondering why my previous slide is not showing. We'll live with that. So, how many of you know what a virtual machine is? Okay. So the virtual machine, what kind of virtual machine system have you used?
Virtual box.
Virtual box, very good. Anybody else?
Virtual box as well.
A virtual box, okay. That's kind of the most popular one because it's open source, freely available. Sadly, Oracle owns them now, but I'm going to get in trouble for this recording. But the idea of a virtual machine is heavy because you have your host OS and then you have a whole layer of the guest OS. So you essentially have two OSs killing your processor. And you fire up one more, you're pretty much guaranteeing smoke from your system, right? So either you have the server or your laptop, you have the host OS, and then you have the VM, and as you fire up more VMs, you are making full copies. Containers are a technology where Docker being an example, where here is the Docker engine, okay? It runs on your laptop, okay? And then when you fire up a container, only the underlying application and the binaries are the new thing. Everything else, it borrows a lot from your underlying host system, okay? And so if you did install something that was common between these two applications, it's only downloaded once. And when you start doing this, what I'll show you, you'll see the Git part behavior where you get chunks of things and then it gets stitched together. And so containers are really awesome. And the cool part of container comes from what's called the union file system. Okay, what the union? Anybody heard of the union file system? No? Okay. So the union file system is you take this and this. Okay. So now if these two guys had that, and this needs it, the union of that is available to that. This one is not making the copies. Okay. So you can have a lot more running without the overhead. Okay. So that's sort of what you need to know about containers for today. We'll talk a little bit more about it. And now I'm going to sort of switch into, and again, full disclosure, Jetstream is one of my projects that got spun off from Cyverse, and I'll tell you why we did that. In Cyverse, when I realized there's a gap in HPC use and the flexibility my users needed, again, keeping in mind I started this project 8-9 years ago, okay? And at that point, Eucalyptus was the cloud system, and now we use OpenStack. But we realized that our users needed a fully customized environment and what I like to call virtual appliances. And the reason I like to call them appliances is that it's like your dishwasher and washing machine, okay? If you want to wash your dishes, you go and put that in the dishwasher. Now, it's surprising how many people don't use their dishwasher the way it was designed, and they wash it and put it for drying in the dishwasher. Different story. You cannot take your dishes and put that into the washing machine, or your clothes washing machine, because soap and water and everything gets churned around, different purpose. But if you know which one to use, you get productivity. You get clean dishes, clean clothes, but not the other way around. Okay? So we realized that we had to change the mindset and the access to technology. Like I told you, always felt we were failing our users. And so we built this new method of managing the cloud infrastructure that was more driven by the concept of, I created this appliance and I want to share it with my colleague. Remember what I said, it's all about sharing and working as a team. And the reason we did that is every lab that we worked with, there would be one person who had that bright idea, would put it together, and the rest of the lab would do a denial of service attack on that person. Because they wrote the code, and everybody wants that code, and then they ask questions of what to do. And for me, the wake-up call was at one of the conferences. We had, at that point, he was a grad student, now he's a professor. He wrote a very nice tool called Callisto. I loved what he had done. So I said, what is the biggest challenge you have? And what are the questions people are asking about this awesome method you're using? He's like, in the 2 years that I've written this, all the questions I've gotten are about how do I install your software. It's like it's uber frustrating. People are not asking me science questions. I wrote this to do cool science, but I feel I've become the tech support of my own software, and I would never want to share my software. And that was really scary for me, because now here is someone who's brilliant, who's putting out good code, has good intentions, but everybody in the community is just after, it doesn't run on my laptop, your code sucks. And he had written it using the best practices for configure, make, by the book kind of work. But so that was sort of the motivation for me to say, we're going to rethink how we do this. And at that point, containers didn't exist, okay? So the project was called Atmosphere, it's still called Atmosphere. It didn't matter how much hardware I bought, we would be out of resources in no time, and I would get the same question. Well, Amazon's never out of resources. What kind of cloud are you guys running? And I'm like, well, if you give me your credit card, I'll make sure that I don't run out of resources. NSF doesn't give me an open credit card. So, we had to sort of rethink how we do that, at which point NSF said, look, you guys could go out and submit an XSEDE proposal for a different cloud, and that's what we did. And I personally don't like to run hardware. If I don't have to, I'm very happy. I love to live in the software layer. So my collaborators at Indiana and at TAC love those things, and I think more power to them. I'm just going to do the software layer. You guys do the hard part of running it. So that's what we did. It allows interactive computing and analysis. It's pretty user-friendly. You guys will get to see it. And then we have pre-configured virtual machines, and then you can extend them. You can put them to use the way you feel like. So what is Jetstream? So it's ease of use, and it is targeted towards the long tail of science. And I know you guys don't fit in that long tail. You're sort of the more advanced users, but when it comes to cloud, I think everybody lives in the long tail because nobody really knows how to use it well enough. It gives command line access for people who want it. It gives a GUI access to people who want it. It supports persistent gateways. There's a lot of reproducibility. So once you create a VM or a virtual machine image, we'll talk about those concepts, and then you store it, you can even push it to IU ScholarWorks, and they'll give you a DOI for it. How many of you know what a DOI is? It's like a document object identifier or data sometimes. You can then put that in a publication, and somebody else can come find that. They can reach Jetstream and even run that computation using exactly the same environment as you had. So there's no two ways about it. Okay? And if they need more RAM or CPU, it's just another click. And that's an important piece to know. Okay? So there are a lot of people who use it. You can go from 1 CPU to 44 CPUs on each system. And they can create their own, even the STEM educators. We have lots of groups that use it. Again, I won't go through that. This is how it looks. Indiana and TAC, they have about 320 nodes with about 15,000 cores that are there. I'm here, the little one. I just do the test and build, and then they do the real running. The platform works. How many of you know what OpenStack is? If you don't worry about it, you're happy. You don't need to know about it. That's Cloud OS. Ceph is the storage, and so Indiana and TAC run that. And then Atmosphere provides the API and the services. It talks to it. It provides the authentication layer. It provides the API, so you can do interesting things with it. But by and large, it's meant for people who want to sort of work at the web layer as well. Here are the specs for it, what you can get. From a tiny to a extra large, which is 44, 120 gigs of RAM, and 480 gigs of storage per request. This is how it looks, and you guys will log in and look at that. The concept here is you launch an instance, you put that into a project, and within the project, you can keep track of URLs, of little, think of it like a thumb drive where you have your storage, and then you can create this project that you can then share with someone. Here you see all your different allocations and how much you are using, how many instances are running. There's a lot of emphasis on making it easy for you to go and do something. Those of you who are trying to follow me, you can go to if you just type in Jetstream Cloud, you'll find the URL. It's use.jetstream-cloud.org. Here you can see the featured images. Featured images are where somebody is doing the curation for you. So if you needed Bio Linux, which contains this, somebody already keeps that up to date as a new version comes out. You are no longer responsible for doing that. If you want R with Intel compilers running on CentOS, it's there. You want CentOS 7.2, all the security patches, everything else is applied for you. When you are in Amazon, it's not fair to sort of compare both. I call this sort of the concierge cloud. There's a lot of thinking that's done for you, and you will sort of realize that, including getting an IP, getting the security, which ports are open per image, which are closed, your login, your password, all of that is managed for you, and it works as a single system. Okay, and we'll jump into that. I have about 15 minutes more. Or,
You can go up to do them.
Yeah.
Okay,
Just
I want
how
you.
much time you want them to.
Okay, I want you guys to have fun with it and be here to answer the questions. So I'm going to quickly walk through and then give you time to pound on this and do cool things. Okay. You can pretty much get direct access on the API. If those of you are interested. And the reason I keep saying sort of access to APIs, you will soon realize that if you're not using automation, you're sort of not really using the strength of cloud. How many of you know what Ansible is? Anybody heard of Ansible? Okay, I'll talk a little bit about that. So when you're launching, 10 machines, 20 machines that can be fully configured, going to each of them one by one is absolutely painful. But you can create what's called a playbook, where you say, here's what I want to do on each of them, and here is the IP for them, go make it happen. This then goes, logs in, configures, sets up, and gets the environment exactly like what you want. So even though I may take a base Linux image, and then I have an idea of how to do certain things, I can create my playbook, and I can give you that playbook and say, you know what, just run this playbook. And as part of your playbook, you might go to GitHub, pull the latest version of the software, compile it, and if something doesn't work, what you should do. So now when you have 50, 60 machines spinning up, you don't have to worry about how you're going to manage them. So Ansible is a very powerful way, and I would encourage you guys, it's just like another shell scripting setup, but they give you a playbook, and if you have time, we'll look at some of those. And then you can log into the VMs directly. You can put in your SSH keys. Now, how many of you are familiar with using SSH keys? Okay, some of you are, some of you are not. And so Atmosphere addresses that, but you can get VNC and SSH to an instance. Now, an instance depends on who's doing what. So let's take a quick sort of walk through with cloud terms. An image is something that is what I call an appliance. So you put everything together. You say, here's my base, which is, are all of you sort of Linux aware? Safe to say? Okay. So you, what's the favorite OS here? What's cool in your world? Is it a Mac floating or?
Yep.
Okay.
That's just what around.
No. But real computing doesn't happen on Mac. Sorry. Sorry. I have one, but no. So Linux, like, whether it's Ubuntu or CentOS, so you would take some base image that you like, put the applications that you want, you configure it, and that becomes your image. So you took a base image, you added stuff to it, now that's your image. That you can put out in the public, and anybody else can come and say, I want to do exactly what Nirav did, find that image, and launch it. When you launch it, it runs, and it becomes an instance. So now you refer to its existence as an instance. And that instance now gets an IP address, it has security policies, it has login. Each instance is all by itself. One instance doesn't know about the other. That's what the OpenStack layer does for you. It gives you that insulation. You just think, oh, it's me and there's no one else around me. But in reality, there are lots of people around you. So if you ask for 2 cores and there are 44, you're friends with 22 other people. And when they do crazy things, it should not impact you, but in reality it does. So if somebody's doing crazy I/O and doing a lot of read and write, and you're like, why is my database query taking forever? And then you look at the disk I/O and it's like, man, I've been waiting for a long time. But it turns out some evil person on that same node. So then you can become a little bit more savvy and say, I want all the 44. I want no one with me. At which point, then you can only blame yourself and no one else, and that's very slow. So those are important parts to note. So you have an image, you have an instance. Okay, are we clear on image instance? Okay. And the last session, you guys learned the most important piece at the end, which was almost forgotten, which was really cool. I was happy because I forget, and then you get a bill for things that you thought you had taken care of. So cloud is the same way. It's like, hey, if you're not going to take care of this, it's not an HPC job where the queue only has 24 hours. We will run you dry till your allocation is over. So it's your job to do the bookkeeping. And that's when, again, something like Ansible comes along and says, let me check all the IPs and see what's the load on all of them and report back to you and say, you know, the 10 things that you spun up, only 2 of them are doing work, the other 8 are just at lunch. So you're like losing 80% of your money right now, wake up. And so those are the kind of things you can automate. That's why I said in cloud, automation is key. Okay, so we've covered that part. Now let's go into sort of when to use cloud and when to use HPC. This is an important piece for you to understand, okay? When you need a lot of customization, cloud is really good. If you don't really need too much customization, HPC systems are pretty nice, and the container technology, the one that we use a lot on our HPC now is called Singularity. It comes from Lawrence Livermore Lab. You can take a Docker container and convert that into a Singularity container. If you go to your university, how many of you have HPC centers at your university? Do most of you use it? Okay. So if you tell them install Docker and they install Docker for you, be very afraid. Actually, they should be afraid because you can hack into the system like in 2 commands. Because Docker runs with very high privilege. So if you're running Docker on HPC, it's just literally 2 commands and you can own your whole HPC system. So don't try anything bad. You can give yourself a lot of allocation. So with Singularity, you can get the same environment. So if you say, I want Ubuntu 17, I'm not sure why you would want that, but if you did, to run my code, you can create a container with that, and it'll run on your HPC system with that. Or if you say, I want Python version 3 with AstroPy, with SciPy, and I need this, I need that, but this version, all of that, you build the container, take it to your HPC system, launch it like a regular binary, it mounts your underlying file system, and then just runs that program. Okay? If you want to do interactive use and you don't care about batch processing, so if you have a Java program or a web app that you wrote, did you guys use a web app in the last few days? Can anybody think of a web app that you used in the last few days? Come on. You guys did something using the web. Huh? Jupyter Notebook. Right? So those are all web-based applications. Okay? Now when you try to run that on your HPC, you are going to like, hey, I need access to port 8080, and they're like, we aren't doing that. And you're like, oh, I know a secret of like port forwarding through SSH through that. But when you're using things like cloud, it becomes really easy, and that's what we'll do. Okay. If you're looking for a parallel file system and you say, here's my container, and I want all the 10 instances to see the same file system, cloud's not for that. But something will tell you that you can do it, but please don't try it. Don't say, oh, I can install NFS on my other things and then mount it. That's just like asking for trouble. Let the cloud be the cloud, let HPC be HPC. Don't try and marry both of them. The babies don't look nice, they're very scary. So bring your own admin if that's what you need. Like, I need root because I'm going to install crap that I'm not allowed on my system. Cloud's beautiful for that. And then if you want anything that is bleeding edge, it's really easy to go to the cloud. And if you need new features, and again, OpenStack does that a lot, so that's the good part. Okay, so how do you get access to something like Jetstream? Okay, you can run a startup allocation. I can tell you within 48 hours you'll get an answer, which is usually a good answer. And I want to remind you guys, when you get a startup allocation, it's not something that's free money, because you have to use that to do real science and then submit for a full allocation. So if you're not going to be doing good bookkeeping of how you use your startup allocation, I've had, now that the project has been live for about 18 months, I've started seeing these tickets. Yeah, I got my allocation, but I forgot to turn off the machine for 6 months, so I couldn't do science. I know, but can't be responsible for that. So, make sure that when you're putting a startup, you think a lot about what you want to do. Jetstream people will help you write that. Because a lot of people are not aware of cloud capabilities, so they'll tell you this would be good to do here or do that. And you don't have to be a prior user of Jetstream. It's a brand new system. So here's secret handshake number 2. The moment you hear that a new NSF XSEDE system's coming on, just send them a cold email and say, I have a job that needs 4,000 cores. Do you guys happen to have that? And they love those emails because they are looking to test and burn systems. And there's an acceptance period. I've had, again, this recording is going to hurt my career. I have used more hours that way on people's systems because they are looking for someone who can come and consume resources. And if it fails, it's okay. And so I'm like, yeah, if it completely crashes your system, I'm sorry if I did that, but if I don't get any results from you, that's okay too, because I have written this in a way where you just tell me where the resources are, I'm going to just go use them. So you guys should do that. And that happens every year, something new is coming up. Like right now, Stampede 2, then there'll be like Stampede 3, there'll be Gordon something, there'll be Bridges something. So in your career, you are going to find time when if you have good code that's doing well and you can give good science output, there are people who are looking for you. So handshake number 2. Actually, I think it's 3. So that said, you get a startup allocation, you just need a current CV, a brief abstract. Education allocation you can apply anytime. I would encourage you guys, if you're teaching a workshop or doing something and you want that, you're teaching Jupyter Notebook and you want to work with 50, 60 gigs of data, you don't want everybody on their laptop to be trying to figuring it out. We have workshops with hundreds of users and it works, and hopefully today also it will work. You just have to give a description of the workshop and do that. The research allocations are quarterly and it's about 10 pages. They give you up to 15 million hour SUs, it's called service units. I've tried for 1 million and I've usually gotten it. But the moment you ask for more, there's a lot more rigor that you have to put in on showing how you're using the system. Okay? And you can see there are a lot of people who use the system. So here's the wiki, jetstream-cloud.org, lots of documentation there. The user guides are there, there's a knowledge base, and then you can always send email to help at XSEDE with questions. So this is sort of coming to the end of my slides before we get hands-on. This is sort of my cloud toolbox. This is what I keep when I need to use cloud stuff. The first is Ansible for automation. Okay. The next is Docker for execution environment. And if I want to send it to HPC, I'll use Singularity. This is sort of my secret sauce. Makeflow and Worky for task distribution. How many of you have had something where, let's say you guys did Jupyter Notebook, so you did parallel IPython, right? You had an assignment on doing that. What was the limitation of that? It was sort of the number of cores you had access to on your laptop. Now you can always like harass someone else and add more cores and give a job to them, but then you are responsible for managing that connection. Makeflow and WorkQueue makes it so trivially easy where, how many of you know what a makefile is? Okay? You can describe your computation like a makefile and say, I want to do this, here's the input and here's my output, here's the program, here are the parameters. And you just write the makefile. You don't even care about the dependencies. If this analysis needs this input but is mentioned here, it will build the dependency graph, it knows to wait for what, and then you submit workers wherever you feel like. They come home, dial to the mothership where it's running, pick up the task, take the input, go run it, bring the output, and deposit it. And if everything crashes, you just restart it. It does the checkpointing for you. It does all of those pieces. So it's really convenient to play with it. And so I've been teaching this in my course for about 6 years now. And the course I teach is called Applied Concepts in Cyber Infrastructure. And it's a project-based learning course. And every year, I take 25 students, and they get a real question. And they're supposed to solve that for the researchers as a team. If they don't solve it, they don't graduate. It's pretty simple. Okay? So 2 years ago, they actually worked on taking code from Jared, who's faculty here, and he had written ClipReduce, and so they added this framework, they ran it in the cloud, and what Jared was taking about 6 months, they were able to do that in 26 hours. Or sort of it was a fairly linear scale out using the same system. So here's the paper, go take a look at it, and nothing in this is about astronomy or specific to that code. You could take any C program, and as long as you can put the binary there and the binary runs on the other system, it's trivially easy. And you can submit workers in HPC, in cloud, and it does all of that coordination for you. So this sort of is my tool chest. If I have to do something that's very involved, where I say, this has to run on Stampede, where it has this version of this and that, then I use another workflow manager called Pegasus. So Pegasus is like my industrial grade. When I have to move terabytes of data, I use Pegasus. When I want to do quick, cool stuff, we use Makeflow WorkQueue, and it has Python binding. So you just write a loop and submit workers. Now, if 100 workers talk to your Python code, it is going to take it down. But because you're using Makeflow and WorkQueue, it has the understanding of what is the worker, and a group of workers has a foreman whose job is to manage those 10 workers, and then you talk to 10 foremen. You don't talk to 100 workers. So all of this sort of complex requirements are handled by it. So it's really a neat system. So go take a look. And the students, it's again, all the developers are undergraduate and graduate students in CS. They've been some of my best collaborators over the years, where you ask them for a feature, next thing you know, in 24 hours, there's like a branch, and they're like, hey, it's available in this branch, go try it out, we've tested it. And so I love to work with them because they're really cool group of people. So now let's do some real work, okay? So there's a piece of paper that went around. I'm assuming everybody has, or each table at least has a login. And the password, the first thing is 0, and after 6, 7, there's an O. It is case sensitive. So go to use Jetstream-Cloud, and I'll tell you what we are going to do, and then we can actually do it hands-on. So before you guys like dive deep in, and then I'll walk around and talk to you guys. Okay? So you're going to go here, get it. You're going to find an image that's called Ubuntu 14.043 with Docker CE. CE is Community Edition. Okay? You're going to then open the web shell once it's ready, and then that's your command line into it. And then I want you guys to go to Hub Docker now. The cool thing is store, and find something that you want to play with. Okay, like oh, I want MySQL or I want Postgres. And we'll see how easy it is to take that and run it rather than try and install all of that and configure it. You just get the container, and then if you don't want it, you destroy it. Now, so a show of hands, how many of you have reached a point in your career where you're installing software and your laptop now is so bloated that the OS needs reformatting and reinstalling? Yes, many hands are going up, and the more you shake your hand, most likely the hardest working, or you just love to install new stuff. So that's where Docker is awesome. You want to try out a different version without taking down everything, without impacting your whole OS. That's the beauty. So you want to try it out, you just bring that in. And remember when I told you about the union file system and pulling things up? Running Docker and running something as the command line is so easy that it's quick. You don't have to wait for the OS to boot up. It's just ready instantly. In the data lab tutorial today, will they learn about Docker today?
We're not going to do anything in Docker yet.
Okay,
Yeah.
but those are the kind of things you guys are bringing in.
That's right.
Yeah. So this afternoon you'll get to sort of see the more concierge version of Docker, but I'm going to show you sort of the more roll your own, roll up your sleeve, do random stuff. And you can install Docker on your Mac as well. But as I just said, installing too much on your OS sometimes makes it unhappy. Okay, so we'll do that. And then what I want you to do is, here's a GitHub URL for a Jupyter notebook where there is a data science notebook with all the dependencies already ready, installed for you to start consuming. And I want you guys to pay attention to one last thing before I let you loose on you melt down Jetstream for me, is the command line. Okay, pay attention to this part. Docker is the program itself. Run is saying just run something for me. -IT is going to say I want it to be running interactively, so just don't run it and exit. This program is going to be staying on. We want the Jupyter notebook available. -rm is an important part. Every time a container runs, it can keep itself in a state where you can just connect back to it, and it starts consuming more resources on disk. So the -rm says when you're done running, just clean up after yourself. Be a good person. Okay. -p is for port. What it is saying is, on this container, I'm opening a port, 8888. That's where my Jupyter notebook is going to be listening. But that container is in my operating system, right? Now you're coming from the outside, and some of you, your Jetstream will run in Indiana, some of yours will run in Texas. By doing this, you're saying my virtual machine, my instance that's running, take port 8088 on that and connect that to my Docker container. That's the connection. That is really important. And this part is the secret sauce that most people don't correctly use. -v is the volume. You're saying, take the directory home train 70, that's the login I'm using, put whatever number you have, and map it to home Jovian work Jupyter. Okay, that's what is sorry, there's a space here, so my bad. Jupyter/data science. So this is taking that and showing it inside the container. So that way you don't have to worry about putting data in the container, taking out. Whatever's your hard drive is visible to the container. Now don't get too greedy and start multiple containers and looking at the same directories. It's not a good idea. And then I'm saying go to Jupyter/data science and bring that container for me. And the cool part is, as the author for that is updating, you can even say :latest, version this. So you can get very fine grained of what you want. And if you run it once, it doesn't have to go back and pull that. It just says, hey, is there a new version? If it is, it'll bring it, because I haven't given it the version. Okay? So this is the key part. So once you log in, anybody has been able to log in? Oh man, you guys are fast. Okay. How many more minutes do I have? About 10 minutes? Okay.
If
We have 20 minutes till our lunch break.
Okay, I would not want to get in between lunch and you guys. Just like that. So, and I'm happy to, I'll be here even during lunch. I would love to chat with you guys about any topic. So no worries at all. So I'm going to now walk through this on my laptop. Any questions of what we are going to do? And you have a terminal, you have a command line, type sudo, do whatever you feel like. Now can somebody tell me what kind of virtual appliance have I provided you here? By reading the name. I gave you an Ubuntu and it comes installed with Docker. Right? So you didn't have to go install Docker. Somebody else did the hard work and gave it to you. You are just coming and saying, I want my Jupyter notebook. Okay? So now let's take a look at that. When Adam just left, the recording stopped. Bad things. I'll save this one. Oh no. Okay, yeah, it is an hour long.